Hi, I'm Mary Beth Lachak, Director of Strategic Communications at the Canada-France-Hawaii Telescope. Today we're talking about Black Holes 101. One of the most frequent questions that I get asked, whether it's by kindergarteners, high schoolers, the general public, is what is a black hole? And after we get into what is a black hole, then I get a lot of fantastical questions about black holes. They're very mysterious for many people. So let's talk a little bit about them today. So what is a black hole? A black hole, really simply put, is a tear in space and time. We have different kinds of black holes, different sizes. We've got solar mass black holes. Those occur when a star that's 8 to 10 times the mass of the sun or bigger reaches the end of its life. It's supernovas, and the larger stars, their core compresses and compresses and compresses and compresses and actually tears space. That's a hard concept to understand. So let's think of a trampoline. If you have one person standing in the middle of a trampoline, it makes a little bit of a divot. If you have 15 people standing in the middle of a trampoline, it's going to break. And so while space is not made of trampoline material, that's one of the easiest ways to kind of understand it and picture it in your head, because this is such an abstract concept. You can also have intermediate mass black holes and supermassive black holes. How supermassive black holes form is one of the really fundamental areas that astronomers are trying to uncover now. How do you go from a black hole that's maybe 10 times the mass of the sun to one that's 4 million or 4 billion times the mass of the sun? So let's look at an experiment a little bit more about black holes, what they do, and some of their properties. This is a gravity well. It's how we're going to understand a little bit more about the basics of black holes. Now, I don't want you to think that space is connected by stretchy material or a trampoline. This is just a way to visualize a really tough concept that exists primarily through mathematics. So if we take a heavy object and place it in the middle of our gravity well, you'll notice that it sags. The heavier, the more materials that we place in there, the deeper the sag. And so with a black hole would be as though I continue to place materials in the center of this gravity well, every time sagging more and more until it broke just in that center region. Now, a misconception about black holes is that they sort of wander through the universe, pulling everything in their path in the way. They don't. Black holes have a radius that their gravity will pull an object into. Objects can stably orbit a black hole, like in some of the movies that you've seen. Interstellar is a good example. If an object gets within the arms of a black hole, I like to think of it in these terms. This is called the Schwarzschild radius. If an object gets within that grasp, it's pulled apart and falls into the black hole. And so that would be similar to if I take the balls here, you'll notice how eventually, because of how deep that gravity well is, you'll notice that the ball eventually spirals in. If I was a really good aim, I could get the ball to actually move across the top and stably orbit it. Now, the reason that objects fall into the black hole but don't come out is because of something called escape velocity. That's how fast an object has to leave a planet, a black hole, or a star based on its gravity. So the gravitational pull, to be able to escape the Earth, a rocket ship has to overcome the Earth's gravitational pull. To escape a black hole, that escape velocity is faster than the speed of light. Einstein tells us that the speed of light is the cosmic speed limit. Nothing can travel faster than it. Thus, nothing can come out of a black hole. Now, a lot of questions that I get are about what happens when objects go into black hole, that energy, that material falls in. Short answer is that's where math goes to die. We're not entirely sure of what happens. There's a lot of hypotheses. The idea that that energy comes out somewhere else in the universe in something called a white hole. There's the idea of a multiverse where objects fall through a black hole and go into another universe or another dimension. all of these are hypotheses. We don't know what will happen because we can't go through a black hole. Now, as that object gets closer and closer to those arms, that Schwarzschild radius, it undergoes a process called spaghettification. And that's exactly what it sounds like. Right now, as I stand here, the gravity on my head is slightly different than the gravity on my feet. Because there's a distance, my head is farther off the ground, farther from the center of the Earth than my feet are. For the Earth, not a big deal. For a black hole, that means that the force of gravity at my feet is much stronger than the force of gravity at my head because the black hole is so much more massive. That distance becomes more important. So I would be stretched out like a piece of spaghetti, or like if you're pulling taffy or slime, and you get kind of that stretching effect. That's called spaghettification. The first image ever taken of a black hole was taken in part here in Hawaii using the James Clerk Maxwell telescope and the submillimeter array. And that was part of this large effort called the Event Horizon Telescope. And they took a picture of the material that was orbiting the black hole in the microwave. The same energy that heats food in the oven, in your microwave oven, a black hole also has material surrounding it in what we call its accretion disk that glows at that temperature. That object, that black hole in the center of M87, a nearby galaxy, was called Poveihi, the embellished fathomless darkness of creation, a name given by Dr. Larry Kimura here in Hawaii, who's a Hawaiian language expert. It's the only image that we have of a black hole. I hope this answers some of your black hole questions. There's a lot of very complicated math that gets involved if we want to probe deeper and deeper into black holes. If you have other black hole questions, please let us know.